So in this talk I will tell you about the problem of defining a complete set of observables in gauge theories, which is a long-standing problem. And I will offer a solution, and it is based on a concept, a new concept that I have introduced in the past years of purely virtual particles. So in the first half of the talk I will introduce that concept, and then I will show you the applications to physics. And in the second part of the talk I will go to the mathematics of defining, using this idea to define a complete set of observables in gauge theories and the implications of that. The nice thing is that you can have also a theory of quantum gravity out of this, and that theory allows you to make predictions. In particular, here you will see the prediction about the so-called tensor to scalar ratio in primordial cosmology. I will tell you later what it means. It's important because it's a quantity that is going to be measured in 10 years. Okay, 10 years ago they said it was going to be measured in 10 years, but
they say now?
In 10 years. So probably in 10 years they will say in 10 years again. And I also stressed during my talk that quantum field theory in physics is not on-shelf just, but it has to be off-shelf, which is very important, also for phenomenological implications. And then I will tell you how this idea enables the construction of a complete set of point-dependent gauge-invariant fields. For example, if you want to define colored states and a scattering of quarks and gluons, or correlation functions of the metric tensor. What is the metric tensor associated with a point? Then you can have an answer from the things that I will show you. Purely virtual particles are particles that are purely off-shell, so they are not on-shell. You cannot observe them. They mediate interactions among other particles. So far I've developed 3 formulations, the first one with Marco Piva, the second and third one are more recent, and I will tell you about the third one, which is probably more explicit in also offering the implication, the price to pay and what you gain. And the fourth formulation is understudy. So this is a diagrammatic formulation. So it starts from high energy physics, Feynman diagrams. You have to play with diagrams because you will end up not using Feynman diagrams, but different types of diagrams to introduce these particles. And the main feature of these diagrams, or combinations of diagrams, is that they are not time ordered. They violate time ordering in a sort of minimal way. Don't take the word minimal in a strict mathematical sense. It's just vague idea, because you could brutally break time ordering, and you break it in some controllable way physically also. So normally you use Feynman diagrams. You will know what the Feynman rules are, but there are many other types of diagrams that you can define. In particular, if you want to study the unitarity equation or optical theorem, it's very important in quantum field theory because you have to ensure that your theory is unitary. It's nice to know that you can formulate that in terms of diagrams that are not Feynman, just Feynman diagrams, but so-called Katkowski-Weltman diagrams, because they are made of 2 parts. Each part is Feynman and Feynman conjugate, S and S dagger. And in between you have what's called a cut. A cut that puts the cut propagators purely on-shell. Because basically here in between you see you are summing on the intermediate states in the scattering theory. So those states are observable and they are on-shell. And if you are familiar with cosmology, in so-called correlation functions are studied. And in that case you have to construct diagrams by doubling the fields and so on and so forth. So can we study all the diagrams in one shot? Yes. So let me tell you how to do it. The ingredients are the usual propagators and vertices. You will not need the conjugates because basically S dagger, you see from this equation, is not independent of S, so that we don't need. But you will need the cut propagators in between, the same I describe you in a moment. So let me introduce them to you more explicitly. This is a cut propagator. It's purely on shell. Theta tells you where the energy flows, and this is the Fourier transform of the correlation function in free field theory of the product. It's not a time-ordered product of two fields, it's just a product. And if you want to apply the Wick theorem to do perturbative expansion, you will have the same analogous formulas with the time-ordered product, with the product, and so you can use the perturbative expansion as usual. And what we want is to build all functions of S that you can construct. So the most general expansion in powers of the S matrix. So the S matrix contains Feynman diagrams, and if you want a product S times S times S times S, you will have a Feynman diagram times a Feynman diagram times a Feynman diagram times a Feynman diagram, and in between you have cuts. So the legs of one and the other are purely on shell, because they are described by this propagator. Perhaps you are guessing where I'm getting to with that, because if those legs are purely on shell, I can use that to define something that's purely off shell by subtraction. And that's the idea. So we want to study all the functions of the S matrix in order to extract the on-shell content of some particle and define a new particle that's purely off-shell. You may think that this complicates things. Well, to some extent it is true, because if you have, for example, 4 points connected in a 3-leg vertex, you don't have time ordering, so you can place the 4 points to the right or to the left of a cut, or in between 2 cuts, or 3 cuts, and so you have 20 possibilities. But for the triangle, you have many possibilities of cutting the internal legs, and so forth. But this is not true a complication, because you see, every time you add a cut, you simplify things, because this propagator is purely on shell. It's kind of easy to calculate diagrams. So if you can calculate this, you certainly can calculate them, all the others. And even if there are many, a computer can list them all. You see there are coefficients here, magic for coefficients, because there is a magic formula that you can work out and that subtracts precisely the on-shell contributions of every particle circulating inside. And so you are sure that your particle will, even if when it circulates inside a diagram, it will be off-shell. So you sum all the possibilities. The cut propagators, which are purely on-shell, are used to define purely off-shell particles, but by subtracting the would-be on-shell contributions of normal particles or ghosts, you can kill the true physical nature of a normal particle, if you don't like it, or a ghost. In that case, you have to kill it. What is a ghost? A ghost is a particle with a kinetic term overall multiplied by the minus sign.
That's a question. So the first diagram is the usual, the Feynman propagator.
Yes.
Like in the textbook. Okay.
And the others, so instead of one diagram, you will have a sum of diagrams. Let me give you some examples. And then you find that there is a magic subtraction formula that does the job. Okay, you cannot use any combination.
Say in the gauge theory, if I do the usual fatigue for both, this procedure will mimic that.
For example, you can use this for the Federico for ghosts. You will not gain much because those cancel.
So just
yeah, I will make the comparison with gauge theories and we'll come to that in a moment. Okay, before giving examples, let me give you some details about this. Basically, it is an exercise of matrices. The S matrix, this is the unitarity equation. Normally, it is written like this, which is called optical theorem. And it is diagrammatically expanded in a sum of Katkowski-Weltman diagrams. You separate the one, the trivial part, from the amplitude. I don't want many eyes around, so let me separate this way. And so you have an identity which is this. This is unitarity in quantum field theory. V plus V dagger is equal to minus V dagger V, with 1, if the theory is unitary. If the theory is not unitary because you want to study a particle with a kinetic term multiplied by the wrong sign, because of your reasons. Then instead of 1 here, you will have a matrix inside, which is diagonal, but has plus, minuses, plus 1s and minus 1s. And the minus 1s indicate that in between you are propagating ghosts on shelf. In between, because these are products, and so the products are that propagator which is purely on shelf. But here you have some minus signs here, and you would like to kill them. So you can say, don't introduce ghosts. Why do you introduce ghosts if you need to kill them? Well, in gravity you have to, for a reason that we will explain. So the important thing is that when you violate unitarity this way, you still have a very important pseudo-unitarity diagrammatic equation which you can work with. And then what you do is just an exercise of matrices, and you can prove that if you replace V or S with a function of V or a function of S, you can clean the minus 1s and possibly some plus 1s. What does it mean? Define a certain matrix A where you have a subset of plus 1s and zeros. And that you will call the projector onto your physical subspace. So physical subspace will be made by a subspace of the plus 1s you have here, the one you like. And then there is this magic formula for a reduced amplitude, which is made of V, A, and B, which is the difference between C and A. It's a certain expansion, and also contains some arbitrariness, an arbitrary anti-Hermitian matrix, which is the most general solution that cleans the equation so that you will have in between A. In between, instead of having C, which had minus 1s, you have A, which has plus 1s or zeros. And then you can play with it. This is just an exercise of matrices. You can verify it yourself. And the simplest option is not good. You will have to determine this arbitrary matrix iteratively in order to preserve the basic properties of diagrams. For example, the reduction of a product should be the product of the reduction, so on and so forth. But basically, there is an answer. So let me give you some examples. But first I complete, and then I will give you the basic examples. So once you have this identity, this A will be the projector onto your physical subspace, and you project everything. So you sandwich the reduced amplitude in between projectors, and you have the projected, the physical amplitude. The physical S matrix will be 1. Now 1 is the projector plus the projected amplitude, and you have unitarity in a projector subspace. So it's like getting rid of ghosts and the temporal longitudinal modes of gauge theories, but without the help of a symmetry here. Since the symmetry is not helping you, I change the diagrams in order to make it happen. And the diagrams will be functions of the old diagrams, but functions that involve products of S-matrix diagrams, Feynman diagrams. And products mean that you have violated time ordering, because a product is not a time-ordered product. Let me give you the basic examples. In my papers you can find all sorts of explicit examples, 1 loop, 2 loops, etc. But the basic ones are, first, the propagator. So if you have a diagram like this, where you have just a propagator, you will have to sum it to a cut diagram, which takes out the on-shell part. So this is the Feynman propagator, which is the principal value plus the on-shell part, and the formula will just tell you to subtract the on-shell part, and you get this. Don't do this. Don't just replace a propagator with this inside Feynman diagrams. That's not my recipe. That option has been studied by Bollini and Rocca. And you will get some entities that are called Wheelerons. Feynman Wheeler, I don't know if you are familiar with that. They are interesting, but they violate unitarity, because you cannot just take the usual Feynman diagrams and change the propagator. You have to change the diagrams into sums of diagrams. For example, this is the bubble diagram. Well, this is the usual bubble diagram, and here you will have a sum of a bubble plus something else, which is simpler. And the final result will be certain integral, that's written here, which is not the integral of, which is not the principal value of the Feynman diagram, which is not that. Okay? It's something else. But you have to work it out. It's simple, but it's not, because you may think that this principal value is purely virtual. That's only true at the tree level. As soon as you put this principal value here, you get on-shell contributions, believe it or not. So you have to do something completely different, which is the recipe I told you earlier. Okay, so you have to make a projection similar to the projection you normally make in gauge theories. You add Faddeev-Popov ghosts and you use all the components of the gauge fields, but then you know that you have some projection later on. And so the classical theory, for example, in a gauge theory is not the gauge fixed. The gauge fixed action is not a classical action. You have to project it. So in this case as well, you have to project even the classical theory you start from, although this projection is not driven by symmetry, but by the idea I'm telling you here. So the classical limit will be the set of tree diagrams where you have in between these purely virtual particles and physical particles only in the external legs. And the propagators in between at the tree level, in this case, they are just the principal values. So let me give you some examples. This is a model that was proposed by Lee and Wick in the 1970. And the idea was to make QED finite. We will use a different idea, but I want to compare their idea to mine, because when you have objects, particles with a negative sign in front, you gain a lot in renormalizability. Here you gain that the theory becomes finite. In gravity, we will gain that the theory becomes renormalizable. That's the point. So this is QED with the electron. I'm simplifying a little bit, but I'm giving you the basic concept. You add a Proca vector multiplied by the wrong sign. And then you couple the Proca vector and the photon to the electron, and then you have a model that's finite with some extra thing. So basically what happens if you want to integrate out the Proca vector because you say it's just a mediator, what you get is something like QED plus an additional non-local vertex. A 4-Fermi vertex that's non-local, and then Lee and Wick calculate radiative corrections because they want to make these ghosts propagate. Let me show you in their paper what they say. So let's say, suppose that after interactions, the mass renormalization terms, etc., after interactions, no stable abnormal particles are left. So they mean that after interactions, these ghosts acquire a width, a lifetime, they decay, and so they disappear from the physical spectrum. And they say, since the S matrix is concerned only with asymptotic states, which by definition consist only of stable particles, such as P, etc., then this is fine. So they want to make these states, abnormal particles, disappear by making them decay. I think that this is very interesting, but it is not a final answer, because first of all, they forget about the muon, and I'm telling you again, physics is not just on shell. The muon, strictly speaking, is not on shell because it decays. And if something is on shell, it must have a definite energy. And if something has a definite energy, by the energy-time uncertainty relation, it takes an infinite amount of time to measure that energy. But if the particle decays, you don't have an infinite amount of time. So the muon is necessarily off-shell, yet you observe it. So you have to have a theory that is able to go off-shell. But anyway, their idea is very, very interesting because it motivated many studies. And in that case, you have a vertex like this. In my case, you have a vertex like this with a principal value. And that changes quantitatively the prediction, but most of all, I don't need the particle to have a width. I don't need that to decay. So that's an important difference, because when I go to the community of people working in quantum gravity, they don't have this background on Batalin, and Frederick Popov, so they do not think of projecting something radically, eradicating it completely out of the theory mathematically. They just think of something disappearing physically. And if a ghost disappears just because it decays, there will always be experimental setup where it doesn't decay and it is still there. So the answer will not be a satisfactory answer. Okay, so the important thing is that we have now something that can be used. For example, let's say in quantum gravity, you will have, this is QED plus a non-local vertex. So in gravity, now I show you, you will have, even in the classical limit, the Einstein theory plus some corrections, but also some non-local, very rapidly oscillating corrections, which have physical implications. How rapidly? The time of oscillation will be 1 divided by the mass of these non-existent particles. And if the mass is sufficiently large, you can be in agreement with all data. Good. Okay, so let's see how to use them for gravity. In gravity, you can start from the Hilbert term, but in primordial cosmology, it's known that if you add r squared, you have inflation, for example, and you even have a prediction for the quantity that I mentioned, the tensor to scalar ratio. So basically, when you have this Lagrangian, you have the so-called Starobinsky model. Starobinsky, by the way, passed away as well a few months ago. And the important point is here you are describing a metric tensor, the tensor, and a scalar field. Indeed, you can add the field explicitly. You can convert this action into an action which is Einstein, Hilbert, plus a scalar field with a very special potential, which is the Starobinsky potential. So what is this R? Tensor to scalar ratio. It's the ratio between the amplitudes of the primordial fluctuations due to the tensor, G mu, and the scalar phi. The amplitude of the fluctuations due to the scalar have already been measured. So I can tell you what m phi is. And the tensor fluctuations are those that will be measured in 10 years or more than 10 years. So in the literature, all sorts of predictions are available for R, in the cosmology literature. From this model, there is one very sharp. It has to be 3 divided by 1,000. Measurements tell today that it must be smaller than 3 divided by 100. So this prediction is in agreement still with data. The point is that this theory is not renormalizable. So it cannot be the fundamental final theory. It can be predictive anyway, because it is not necessary to have renormalizability to make predictions. And so you have this kind of thing. This as a problem. The problem is not renormalizable. So if it is not renormalizable, all sorts of other non-renormalizable models circulating in the literature. Everybody has his own prediction for R. But this doesn't take advantage of the huge constraints that come from high energy physics, because if you want unitarity and normalizability, normally you don't have many possibilities. You have just one. So let's see if there is one possibility for gravity. So the idea is to proceed as in the case of the Fermi theory of weak interactions, where you had an interaction of 4 fermions, and blew it up by means of intermediate bosons. Now they will be intermediate purely virtual particles, because you cannot solve the problem with intermediate things. Those would have to have a minus sign in front of the kinetic term. They would have to have ghosts. So the point I want to make is that if you want a prediction that's more robust than those circulating in the literature, you need to use the constraints of high energy physics, and you need to propose a theory of quantum gravity. Otherwise, you cannot get out of this. So the proposals of theories of quantum gravity in the literature are infinitely many. I will not comment on them because most of them do not make predictions. I will just comment on string theory, going back to what I said so far. Remember that string theory is only on shell, and being only on shell, I do not regard it as an adequate candidate to be a fundamental theory of the universe, because this is a fundamental flaw of the theory. You need a theory that goes off shell as well. The other thing is that if you want a theory of quantum gravity, you cannot make Pindaric jumps. You have to be extremely conservative and tweak what was successful so far, like the standard model, as little as possible. So that's what I'm doing here. So you start from the Starobinsky model and add the square of the Weyl tensor. The cosmological constant is there because renormalization turns it on, but you will not find it very important for primordial cosmology. This adds a new parameter, mchi. We will be able to make predictions anyway. And then you have a theory that's made of three particles: the graviton, the Starobinskian, if you want, and the additional thing. The gain is this theory now is renormalizable, because the additional object, as in the Lee-Wick Broca field, here it is a Pauli field, spin 2 particle with the wrong sign in front of its kinetic term. If you remove the higher derivatives and get to these three fields explicitly. Okay, so you have something else, and the point is that if you interpret the diagrammatics of this theory as you would normally do, then this theory propagates ghosts inside. So you can do all sorts of things that have been proposed in the literature, like Lee-Wick and so on and so forth. I propose, of course, to treat this additional spin 2 as a purely virtual particle. And a bonus is that this extra parameter has to be bound by this inequality to be related somehow to the mass of phi, which is known, and therefore, even if it is mchi not known, the prediction will be still very sharp. So I will tell you in a moment. So what happens basically, that this additional particle is a fake particle, and therefore you have to integrate it out in diagrams with the rules I told you earlier, 3 diagrams. It's like this. To tell you what happens, let me show you what the principal value of 1 divided by p squared minus m squared is. Just for time dependence, it is an oscillating function. Very rapidly oscillating, depending on your mass. If the mass of the intermediate particle goes to infinity, you have a delta function, and the 4 Fermi vertex becomes local. So basically, it's like saying that the classical theory of gravity is general relativity plus the Starobinsky term plus very rapidly oscillating non-local corrections that we do not see because they average to something we don't see. Then you can ask, how rapidly do they oscillate and why can we see them? I will tell you in a moment. And I skipped this because it is taking too long, but anyway, it's important to notice that you will have this bound for the mass of the spin 2 purely virtual particle from cosmology, and to study the consistency of purely virtual particles in cosmology, you find this kind of bound. So let me give you the numbers. You find a prediction for the tensor to scalar ratio. This is it. So since you have an extra parameter, you cannot make a prediction that is just one number, as in the Starobinsky model. You have a window, but because of the bound that I just told you, the window is so narrow that in 10 years it will not be possible to distinguish between my prediction, this window, and the Starobinsky one. So basically I'm telling you Starobinsky was right 50 more years ago. And maybe one day we will be able to distinguish where we are exactly inside that window. But I have to be very, very lucky to hope for that happening before we die. And then you can compute all sorts of other quantities that will be hopefully one day measured, because once you have the theory, you can compute quantities. That's just to give you an idea that this kind of things works, but we want to also tell you the price to pay. You don't have to renounce normalizability, you don't have to renounce unitarity. What you renounce is having a temporal ordering. Because since you have violated time ordering, you cannot say what present, past, and future are anymore. Where? Within this local, non-local vertex. So numerically, you find that this mass is 10 to the 13 GeV from the spectra of scalar fluctuations. M chi is of the same order or bigger, and that means that 1 divided by M chi is a time 10 to the minus 36 seconds. So anything I'm saying applies to intervals of time that are shorter than 10 to the minus 36 seconds. Which are the times of inflation? You can ask what is the most precise, the shortest time ever measured so far as time. That is 10 to the minus 18. So we are very, very far away from that. And even if you have this violation of temporal ordering, let's say you cannot classify events as past, present, and future, that's compatible with all data, because we don't even know if there is a time below 10 to the minus 18 seconds. And the comparison with gauge theories is something I have already said something about, because normally you have also to consider additions to a gauge theories that are have their own statistics, like the Faddeev-Popov ghosts, or are propagating states that are physical. And then you know how to apply the machinery in order to get rid of them. You do not consider scattering processes between Faddeev-Popov ghosts. Ghosts are ignored outside an amplitude, and they do not appear inside as a bonus. So that's unitarity. They are not generated inside the diagram. So you neglect them outside, but they do not appear inside no matter what you do, because there is a symmetry protecting them. Here I wanted to kill something without having a symmetry that protected me, and I had to change the diagram, the very definition of diagram. Fortunately, the solution existed. So that's the thing. And then you can show that you can go on shell, off shell, and still prove a unitarity equation for the evolution operator in quantum field theory, diagrammatic equation. You will violate this product, this property here, which is the mirror of the violation of time ordering. And you can do some phenomenology, with some group in Tallinn we discussed, model building. You will see some differences in peaks or resonances. Let me go to the problem of defining gauge-invariant fields. This is a problem that dates back to Dirac, I would say, because Dirac was not satisfied with having to work with an electron that is gauge-dependent. So you see in his paper, gauge-invariant formulation of quantum electrodynamics. He wanted to have a gauge-invariant formulation of quantum electrodynamics. So how do you define the correlation function of two electrons? Psi bar psi. Psi bar psi. This is gauge-dependent, and if you compute it, you will see that it depends on the gauge-fixing parameter. If you go on shell, scattering matrix, asymptotics, again, you can get rid of the gauge dependence. Or you can consider gauge-invariant operators, like psi bar psi in the same point, like f mu squared. But these are non-linear, so you are missing something. You understand that probably your set of observables is incomplete. You should have a linear set. And his idea was this, to dress the electron with a cloud, which is this exponential here. exponent of that. And then you can check that this object is gauge invariant. So if you make a gauge transformation of this, it's 0. It's non-local. It's kind of strange. If this is a Laplacian, you're also violating Lorentz invariance. That's less serious than you may think, but still at this level is kind of annoying. And another thing that I want to emphasize is as follows. You could use a different object like this, fully Lorentz invariant. But then you would need a prescription to define this object, one of a box, and that turns out to be a ghost. That's why Dirac doesn't do that. Others have generalized this to non-abelian gauge fields, 1985-66. More recently to gravity, you can do that. But they all are kind of unsatisfactory because either you have ghosts or you have this awkward object. Being non-local is not very disturbing. As long as you have 1 over box and it is well prescribed, you can live with that. But being 1 over Laplacian is something that deserves some attention. So there is one thing, however, that's very, very good about this thing. It's 1 over Laplacian. It's purely vertical. Because 1 over Laplacian doesn't propagate anything. So what you need is just a generalization of 1 over Laplacian, something that remains purely vertical, but at the same time does not break Lorentz invariant. And this is what the concept of PVP does. So let's see what we gain by doing that. Let me also tell you how this kind of problem has been phrased in classical gravity now. Classical gravity. It dates back to 58. Construction, you see, of a complete set of independent observables in general theory of relativity. How do you define observable in general relativity? You have to integrate over all space-time. Is there some point-dependent? Well, point-dependent in some sense, yes. You can do the following thing. You take 4 scalar fields, any scalar fields, phi 1, phi 2, 3, 4, and you assume that you can invert phi of x into x of phi. Phi of x, x of phi. At that point, you will have that x is always a function of 4 scalar fields. Could be matter fields, could be probes, could be anything. And then when you insert that into a 5th scalar, any other scalar can be rephrased as a function of not coordinates anymore, but physical objects, the 4 scalars. Physical, well, let's see. So these 4 scalar fields can be used to define observables or some reference entities that then allow you to define observables. Somebody speculates about a sort of ether of GPS, or you could build these 4 scalars with gravity itself. It's not necessary to think that these 4 scalars are extra matter. They could be r mu nu squared, r mu nu rho sigma squared, any 4 scalars. And then you have to do this thing. So you will have some non-local definition, but still it could work. So in my approach, as I told you, I just take these ideas and explore the possibility of building observables by covariantizing everything and getting rid of the ghosts by treating them as purely vertical particles, which means that basically you have to think that in the universe there is an ether of pure virtuality that allows you anyway to define new correlation functions in the theories without changing the theory. So let me stress it again. When you have 1 over a box, it could be a ghost, but anyway, even if it were not dangerous, you are changing the theory, because this is an extra degree of freedom. You cannot do that. You have to change as little as possible. And the proposal that I make is this one. So basically, you do as follows. I don't want non-local things around, and so as usual, I introduce extra fields, and I will get rid of the extra fields later, so no non-local things that are explicitly around till the very end or whatever. So you introduce extra fields phi in the adjoint. You build the exponential, and you use that exponential to compensate the gauge transformations of the fields, and you dress the fields like this. You postulate a suitable gauge transformation for the extra fields, and then you prove that the dressed fields are gauge invariant. You can do that for gravity. This is known. Okay, so the problem is that now you have extra fields, and extra fields change the theory. You want to get rid of the extra fields, so you postulate a trivial symmetry. You add other extra fields, the ghosts for this symmetry. I will call this the cloud, ghosts, cloud fields, cloud symmetry, and so on. And then you will have to use a sort of fixing, a cloud fixing for these symmetries, which in this case is just this function here. You will be able basically to mirror everything you do for the gauge fixing for this dressing. But let me show you where I want to get to. So I add fields, but since I don't want to add fields, I add more fields, and I add a symmetry that's supposed to kill everything. And in the end, for example, your complete solution to the Zinchenstein-Master equation would be what? F mu squared, fermions, usual gauge fixing, and usual Faddeev-Popov ghosts. And then you have a mirror gauge fixing, which is the cloud fixing for a certain function that will fix the dressing. E is an auxiliary, like field. And then the Faddeev-Popov determinant of the partners of that. And then you know that you have to collect all the symmetries in the solutions of the master equations. So K are the sources for all the transformations. These are the transformations of the fields, the ghosts. And then you will have the gauge transformation of the new fields and the cloud transformations, which are trivial. And then you will have, as I said, a mirror of the gauge fixing, which fixes these dressings, and the Faddeev-Popov determinant. So you can tell me, so far you have done nothing. It's the usual trick of introducing 1 in the functional integral. Indeed, I've done nothing. And one good thing is stressed here is that you can dress each insertion into a correlation function with a different cloud. But at some point you have to break the symmetry. So now I will tell you what I'm going to do. The theory is at the level of the action absolutely equivalent to the theory I start from, which is still QCD. But I want to consider new correlation functions, which are correlation functions of fields that are gauge invariant only. So let me repeat. I introduce new fields. To get rid of them, I introduce other new fields and an extra symmetry. This extra symmetry is a gauge symmetry. I break that symmetry. Otherwise, I do not get anything new. So I'm breaking a gauge symmetry, the extra one, not by breaking it brutally in the action, but by considering insertions in correlation function, just insertions. They will break the extra symmetry. Because the insertions are gauge invariant, but not invariant under the extra symmetry. And these are colored quarks, colored states, for example. I want to study the electron, positron scattering, off shell. How do I define an electron and a positron off shell? They are gauge dependent. These are not, because they are dressed. But since I am breaking the extra symmetry, I take a risk here, because breaking the extra symmetry, which is a local symmetry, I normally propagate ghosts. And that's what normally the breaking of a local symmetry does. We are again back to the problem of the Dirac thing, that this will be basically a box, and it will be a ghost. So to make the story short, you have to treat the entire extension, clouds, cloud fixing, extended fields, as PVPs. Then that's it. And then you do not propagate anything new, you do not break unitarity, you do not propagate any ghosts. And so this is a recipe to construct new gauge-invariant quantities, purely off-shelf gauge-invariant correlation functions in a quantum field theory of your choice without changing the theory. Let me show you some examples. So for example, if let's say in a gauge theory, the stress field, the fermion, is some expansion. If there was an exponential, to the lowest order it is just this. The gauge field is something like a mu minus d mu phi, then there is something else. The cloud fixing is something like this, plus for the Epopov determinant. You put everything inside, you work out the propagators, and then you will see that the two-point function, for example, for the fermion, is the usual two-point function plus extra contributions. This is the usual one, extra contributions, because now you have these extra fields. And so you have that. The important thing is that this construction is fully perturbative, because I want to insist on that. I'm not claiming that I can do non-perturbative black magic, as some people claim to be able to solve all problems with. So the undressed two-point function is this. The dressed two-point function is basically the same. There is a duality between gauge and clouds. So basically the gauge fixing parameter is replaced by the cloud fixing parameter. This parameter here, in front of the cloud fixing function. And then a way to probe if the theory is unitary or not is by going back to the optical theorem, which is studying the absorptive part, which is the real part. And you will see that the real part is positive, very nice, positive, but it's multiplied by lambda tilde, which is this arbitrary parameter, which can be positive or negative. So it is not non-negative, you are propagating ghosts. This is no good, not a meaningful correlation function. And this comes from the fact that I am calculating here the extra diagrams with a Feynman prescription, not mine, the PVP, but a Feynman one. What changes when you do the calculation with purely virtual clouds? Well, let me show you the gauge fermions in the two cases in a smarter gauge, which I call special gauge, where the gauge fixing parameter is inserted also in front of D0, A0. This is a very important thing because you gain a lot, and I will show you. And the cloud fixing will be the same with gauge invariant fields and in a new parameter, lambda tilde. Then you work out the propagators, and you will see that this nice gauge fixing and cloud fixing function, pair of functions, is able to clearly isolate all types of poles. These are the physical poles. Then you will have gauge poles, they depend on the gauge fixing parameter, and cloud poles that depend on the dressing, and those depend on the dressing parameter, lambda tilde. So these are the physical poles. You have to prescribe them a la Feynman. There is nothing you can do about them because those are physical particles. But here you will see p hat This tells you that this part of the propagator is the gauge-dependent one, is a gauge trivial mode, gauge trivial, and gauge trivial, and this is cloud, and this is cloud. And then you have for the Popov ghosts, gauge, the ghosts of the cloud, depend on the cloud, and so on. So once you have clearly distinguished all of them, you know which one to treat one way and which one to treat differently. And the physical quantities are gauge independent, so you can treat the gauge trivial poles the way you like, as long as you treat all of them the same. They will compensate inside, so you can treat them, all of them, as Feynman or purely virtual. But the point is that these poles here have to be treated as purely virtual. And then the difference between the non-PVP approach and the PVP one is that in the PVP one, the absorptive part loses the lambda tilde in front and is now non-negative. Okay, this is just a matter of calculation to check that by means of this new diagrammatics, I have removed all the on-shell contributions inside the diagrams from the particles that would be ghosts, and therefore I do not have any disturbing content. And this is why I claim that this is a viable thing to define these objects. You can do it for the gauge field 2-point function. See, I have only 5 minutes. 10, okay. But I will leave maybe minutes for questions towards the end. And another approach that I want to comment on is Wilson lines. With Wilson lines, you can also define correlation functions of gauge-invariant correlation functions. But if you want to do this exercise, for example, in QED, you compute the 2-point function of a fermion, and you put a Wilson line between psi bar and psi in order to make it gauge-invariant. You check the absorptive part, negative. Wilson lines do not preserve unitarity. And they are very bad for many other purposes because they are Wilson lines. You can make perturbative calculations, yes, but they are very, very annoying because you are integrating on X. So they are not the standard perturbative diagrams. And so I think that what these constructions I offer permit is kind of interesting, because basically you can define a gauge-invariant field without breaking unitarity that depends on the point. Although it is kind of non-local, it depends on the point, not on the line. Wilson line depends on a line. It's highly, highly non-local, or Wilson loop. Here you have, for example, a G mu nu, an observable metric tensor that depends only, which is dressed on the point. Okay, so what is the meaning of this? You have a complete set of gauge-invariant fields that we can handle perturbatively with the usual rules of diagrammatics, plus the recipe to treat certain things as purely virtual. What we have done is to break the global gauge symmetries without breaking the local ones. So unitarity is still there. Why do I say I'm breaking the global gauge symmetries? Because I am considering correlation functions of colored states, for example. A colored quark, a charged electron. That breaks the global symmetry at the level of the single insertion. But the correlation function overall is still gauge invariant, even globally. So it's like saying you have only scattering that conserves charge overall. But the scattering can involve charged particles. You don't need neutral particles. You don't need singlets in QCD to define an off-shell correlation function now. You can study colored objects. But the global symmetry will be not broken. Unitarians prefer. What can we use this for? the important thing is that you can do something off-shell. What is the meaning and the arbitrariness intrinsic in this construction? You have this dressing. Is it arbitrary? Yes. Is it infinitely arbitrary? Yes. I just showed you the simplest power counting renormalizable dressing, but there is an infinite arbitrariness. Should it be arbitrary? Yes, because it describes the interplay between the phenomenon and myself. I am classical, so the classical environment is infinitely arbitrary, and there should be infinitely many parameters. And some of those parameters can be handled by making some probe measurements, and then everything else is predicted. But the fact that there is an arbitrariness here is intrinsic in the construction. It has a physical meaning, and it also allows you to gauge fix or to describe, dress your particles differently. For example, if in a scattering process at CERN you have a photon in that direction going into that detector, you don't need to gauge fix that one with the same gauge fixing you use for another photon that goes into another detector. You can dress them differently and really describe better fitting to the experimental apparatus. Okay, so the goal is to go off shell and study interactions. I don't know if they can be called scattering, maybe yes, scattering doesn't need to be on shell. And certainly you cannot call them asymptotic states, but still they are quantities that are maybe useful could be useful in applications where you do not have the possibility of having asymptotic physics, quark-gluon plasma, for example, and so on and so forth. Probably this is the end. No. Oh, the extra parameters, I've told you about those already, the arbitrariness. And so that is it. Yes. Thank you.
Questions? Yes.
I have a couple of questions. One question is the following. It is well known that in the theory of cosmological perturbations, there exists, at least in the linear order of this perturbation theory, there exists the class of well-defined gauge-invariant observables, Bardian observables. And they can be extended to higher orders of perturbation theory, at least, well, perturbatively in the long wavelength limit. So the first question is, to what extent, how these variables are included, if they are included at all in your construction?
This is something that I have to check. Because yes, that was raised to me, this question, and it deserves to be considered. But right now, I'm not so, I don't know that much about those to anticipate the answer. But the answer will be whether they will be the same or whether they will be functions of these. So I cannot tell you.
So you think that these variables introduced by Bardian and other people, they actually rely on different, so to say, strategy, different
Yes. So if this thing is complete, certainly any other approach will then be it will be possible to express every other observable as a function of these, but the function might not be same.
Okay, so maybe if I can, I would ask the second question. So you talk a lot about extension beyond off-shell extension. But it is well known that the off-shell extension of the effective action is not unique. So in your picture, it seems that there should be the same level of non-uniqueness. Simply, well, one can pose, and the construction of your observables gauge-invariant quantity can be converted into a gauge-invariant one if it is also supplied by the gauge condition in which this definition of the observable is given. And then the question arises how to associate this auxiliary gauge conditions with the physical interpretation of these observables. So it would seem that the same level of complexity would still remain in your construction.
Yes.
Maybe you have some.
Yes, so that's what I was trying to explain again. So first of all, there is this arbitrariness. But I want to interpret physically this arbitrariness by telling you what to do physically to fix these parameters. So my analogy is, I don't know if you are familiar with infrared divergences in quantum field theory. When you have infrared divergences, you can define observable scattering processes in gauge theory, but you need, for example, a resolution. The resolution of your apparatus goes into the physical prediction. That's very clear, how a new parameter is interpreted physically. But there are other situations where you don't know that clearly. For example, there are soft divergences, clear. Collinear divergences are less clear. There you need an angular resolution. That's much more difficult to relate to experiments to the extent that experts told me that you have an extra arbitrariness. How do you get rid of that? You make one initial measurement, you fix it, and then you go on. That's the easiest way that I apply here. So I have many parameters. This tells me that the correlation functions will depend on them. I have an extremely hard time understanding what the physical meaning is of each, but I know that they are related to my apparatus. I don't ask myself what the single meaning is. I just make a certain number of initial measurements that allow me to fix the parameters I need, and then, after paying that price, everything else is predicted. So the good thing is that there is this huge arbitrariness of clouds, a subsector which is singled out by a finite number of arbitrary parameters, which is the one that is strictly normalizable, because you apply and then you can ask me, okay, but what is the physical meaning of the parameters that go into the strictly normalizable dressing? I don't know. Just know that there are finitely many, and if I can manage to create a physical situation where only those are interested, I know that after a finite measurement, number of measurements, I can make predictions. That's what I would suggest. As far as I know, only in the case of soft infrared divergence, you have really clear interpretation of the extra parameters that needed to introduce in order to get to the prediction. I don't know if this answers the question.
Maybe the last technical question. Is it right that your PVP description regarding this physical observable is basically designed in order to circumvent the problem of non-locality of this observables which you get? Because they are not local anyway.
Yeah, they are not local anyway. It's a kind of way to control non-locality. I think that having non-localities in gauge theory is always something you have to deal with, because unless, as soon as you gauge theory, you have to do something that is kind of non-local. So I'm not scared at all about that, but certainly there could be physical situations where these non-localities might be interesting to study. I don't want to get rid of non-localities. Just want to tame them in a certain way and then compare to experiments.
Okay, thank you very much.
Thank you. So, any other urgent questions? Okay, if not, let's think again.